On the 12th of April, 2003, a United States Air Force captain was flying her attack aircraft over the Iraqi capital when a surface-to-air missile detonated directly beneath the rear section of her plane. The explosion drove hundreds of metal fragments through the fuselage in the fraction of a second it took the pressure wave to expand and dissipate. Both hydraulic systems were severed simultaneously. The rudder stopped responding, the control surfaces locked in position. A thick trail of smoke began pulling from the damaged tail section, visible for miles against the desert sky. Every other combat aircraft in the American inventory, placed in that precise set of circumstances, would have become an unguided projectile at that moment. The pilot's remaining decision would have been how quickly to reach the ejection handle before the aircraft's attitude became incompatible with a survivable ejection sequence. The aircraft would have been written off. The mission would have ended in a parachute descent over hostile territory. The captain did not eject. She reached for a manual control switch that most combat pilots never touch in their entire careers because the systems it bypasses never fail. She engaged it, and her aircraft, stripped of every electronic and hydraulic assistance system that modern aviation depends on, became flyable again. Not easily flyable, not comfortably flyable. Every input to the controls required physical force that the hydraulic systems had previously multiplied into mechanical action. She was flying the aircraft through direct muscle effort against the resistance of control surfaces that were never designed to be moved that way. She turned the damaged machine toward friendly territory and flew it for an hour. When she landed at her base, the ground crews who examined the aircraft counted damage that, by any reasonable assessment, should have been fatal to the mission and to the pilot.
The number of individual penetrations in the airframe ran into the hundreds. In the rear fuselage, where the missile had detonated, there was an opening large enough for a person to climb through without ducking. The aircraft was the A-10 Thunderbolt II. The soldiers on the ground who had watched it work across 3 decades of service had given it a different name, the Warthog. And the story of why that name fit, and why a machine that looked like an engineering accident became one of the most operationally significant aircraft in American military history, begins not over Baghdad, but in the planning offices of the Pentagon in the late 1960s, where a group of analysts was staring at a map of Central Europe and calculating how many armored vehicles the Soviet Union could push through a single geographic corridor before the West ran out of ways to stop them. The corridor in question was a stretch of lowland terrain in central Germany, a natural avenue of advance that military planners had identified as the most likely axis for a large-scale Warsaw Pact offensive into Western Europe. The terrain favored armored movement. The distances were manageable, and the American analysts who ran the numbers on Soviet armored strength concluded that the volume of vehicles that could be committed to an offensive through that corridor in the opening days of a conflict was staggering. Potentially many thousands of tanks and armored personnel carriers moving simultaneously, at a pace that would overwhelm any static defensive line and strain the response capacity of conventional air power to its limits. The problem with conventional air power against massed armor was not capability in principle. Fighter bombers could kill tanks. They had been doing so since the Second World War. The problem was the geometry of the threat. A fast jet attacking from medium altitude needed to approach its target, complete a firing or bombing run, and depart before the dense anti-aircraft environment around a modern armored formation could engage it effectively. The combination of approach, attack, and departure consumed time and distance that, multiplied across thousands of individual sorties against thousands of individual vehicles, produced a mathematical reality. The aircraft available could not kill armor fast enough to stop the kind of attack that Soviet doctrine described. What was needed was something different in concept. Not a high-altitude aircraft making brief passes through the threat zone, but a low-altitude aircraft that could operate persistently over the battlefield, close enough to the fight to identify individual vehicles, distinguish friend from enemy, and engage with the kind of precision that distance made impossible. A slow aircraft, a low aircraft, an aircraft that flew, in the words of the officers who wrote the requirement, in an environment where every soldier with a rifle could take a shot at it, every anti-aircraft gun was within range, and every shoulder-fired missile was a potential threat. The logical implication of this requirement was uncomfortable but unavoidable. An aircraft operating that slowly and that low over a defended battlefield was going to be hit, repeatedly, by everything. The design philosophy could not be based on avoiding damage, because damage was a certainty rather than a contingency. The design philosophy had to be based on surviving damage, on building a machine that could absorb punishment that would destroy any conventional aircraft and continue flying, continue fighting, continue supporting the soldiers below who depended on it. In 1966, the Air Force launched a formal competition for this aircraft. The program designation was straightforward: an experimental attack aircraft that would be evaluated against the specific requirements that the European armor threat had generated. What was not straightforward, and what set this program apart from nearly every other aircraft development effort in American history, was the sequence in which the design decisions were made. Normally, an aircraft begins with an airframe. Engineers define the size, weight, configuration, and performance envelope of the platform, and the weapons it carries are selected and integrated afterward. The attack aircraft competition reversed this sequence completely. The primary weapon was chosen first, and the aircraft was then designed around it. The weapon that drove the entire program was a rotary cannon of a scale and power that had no precedent in aircraft armament. 7 barrels, arranged in a rotating cluster, driven by a hydraulic motor, capable of firing 30mm projectiles at a rate that made individual rounds acoustically indistinguishable from each other. The weapon produced not a series of distinct shots, but a continuous tearing sound that became one of the most recognizable audio signatures in military aviation. The physical dimensions of this cannon were extraordinary for an airborne system. Its length approached 6 meters. The drum that fed ammunition to the rotating breech held over 1,000 rounds, each projectile approximately the size of a wine bottle and weighing nearly as much as a brick. The entire assembly, loaded and ready, weighed more than the average automobile. 6 companies submitted proposals for the aircraft that would carry this weapon. The field was eventually narrowed to 2 designs that were direct competitors in flight testing during 1972. The contrast between them could not have been more complete. One competitor presented a conventionally attractive aircraft. Clean lines, a single tail fin, the kind of aerodynamic elegance that characterized contemporary military aviation, and communicated visually that this was a serious and capable machine. It looked like what people expected a modern combat aircraft to look like. The other competitor looked like something assembled from the leftover components of 3 different programs. Angular, where the other was smooth. Asymmetrical, where convention demanded symmetry. 2 engines mounted high on pylons above and behind the wing, rather than integrated cleanly into the fuselage, or pod-mounted below the wing, where they would have been more aerodynamically efficient. A twin-tail configuration that belonged conceptually to a much larger aircraft. No attempt had been made to optimize the visual presentation of the design for the evaluation panels or the cameras that would photograph it for press releases. The aircraft looked, to multiple observers who recorded their first impressions, like something produced by people who had never been told that aircraft were supposed to look a certain way. Those observers were correct in their perception. The people who designed the ugly aircraft had explicitly not tried to make it look like a conventional combat airplane, because making it look like a conventional combat airplane would have required making the engineering choices that conventional combat airplanes made. Choices that optimized for speed, agility, and radar profile at the direct expense of the characteristics that the close support mission demanded. Every feature of the ungainly design was the direct product of a specific survival requirement, and the survival requirements drove the aesthetics rather than the other way around. The engines mounted high on pylons behind the wings, rather than in a more integrated and aerodynamically efficient position, served three simultaneous purposes. From the perspective of observers on the ground, including observers with shoulder-fired missiles seeking a heat source to track, the wing surfaces shielded the engine exhausts from direct line of sight below and to the sides, reducing the infrared signature that heat-seeking weapons depended on. The exhaust plumes were directed upward and away from the aircraft's belly and sides, dissipating into the airstream above the tail, rather than presenting a concentrated thermal target beneath the fuselage. And the elevated position of the air intakes meant that the engines breathed from well above the ground surface, avoiding the ingestion of debris that ground-level intakes would inevitably encounter on the unprepared forward airstrips that the aircraft was designed to operate from. The twin tail fins served a purpose that only became fully apparent when the aircraft fired its cannon in sustained bursts. The recoil force generated by the weapon at its maximum rate of fire exceeded the combined thrust of both engines, meaning that firing the cannon while reducing power to maintain airspeed would, if uncorrected, produce a braking force greater than the aircraft's ability to maintain level flight. The twin-tail configuration provided the lateral stability necessary to counteract the yawing moment that this recoil generated, keeping the nose pointed at the target rather than swinging away from it under the mechanical force of its own weapon. The evaluation results in late 1972 confirmed what the design philosophy had predicted. In the specific missions that the competition was designed to test, low-altitude attack, resistance to ground fire, operation from minimal infrastructure, the ugly aircraft outperformed the elegant one in the ways that mattered. The contract went to the company that had built the machine that looked like a compromise, and the A-10 Thunderbolt II entered development as a production aircraft. The integration of the rotary cannon into the airframe produced an engineering challenge that the designers had anticipated in principle, but whose specific manifestations required solutions that nobody had developed before. The cannon was mounted on the aircraft's centerline, a decision driven by pure physics, since any lateral offset of a weapon producing that magnitude of recoil would generate a turning moment that would make accurate fire impossible. The barrels extended forward of the nose, giving the aircraft its characteristic profile. The drum of ammunition occupied a substantial volume in the forward fuselage, leaving the design team with the puzzle of how to route all other systems around a cylinder that claimed the space most aircraft used for electronics, fuel, and landing gear mechanisms. The landing gear solution that emerged from this constraint was itself unconventional. The main gear retracted forward and slightly outward into pods at the wing roots, rather than rotating rearward into the wing itself, leaving the gear doors and strut fairings visible
as slight protrusions below the wing surface, even when fully retracted. This was not an aerodynamic oversight, but a deliberate choice with a specific survival function that will be discussed shortly. In 1978, during a test flight intended to evaluate the cannon system under various firing conditions, the pilot engaged a firing sequence, and the cannon performed exactly as designed. What happened next had not been predicted. The combustion gases and unburned propellant particles expelled from 7 rotating barrels in rapid sequence formed a dense cloud that expanded forward and to the sides of the muzzle, directly into the path of the air intakes on both sides of the aircraft. The engines, suddenly presented with an atmosphere depleted of oxygen and contaminated with combustion products, flamed out simultaneously. Both engines, at the same moment.
In a test aircraft that had no ability to restart them quickly enough to prevent an uncontrolled descent, the aircraft was lost. The incident forced a complete reassessment of the propulsion weapon's interface and produced a series of modifications that took years to fully implement. A deflector system was developed to redirect a portion of the gun gases away from the intake path. The propellant chemistry of the ammunition was reformulated to reduce unburned particle output, a change that addressed the engine contamination problem but introduced a secondary effect in which combustion residue from the modified propellant deposited an oily film on the pilot's canopy during firing sequences, obscuring forward visibility at the moment when the pilot most needed to see the target. The solution to this problem was a windscreen washing system, a spray nozzle and fluid reservoir that the pilot could activate during or after a firing run to clear the canopy, operating on the same fundamental principle as the windshield washer on an automobile, which is perhaps the most mundane engineering solution ever incorporated into a combat aircraft. The final modification addressed the root cause of the engine flameout problem rather than its symptoms. A continuous ignition circuit was wired into the engine control system that activated automatically whenever the pilot pressed the firing trigger. If combustion gases entering the intake caused the flame in a combustor to extinguish, the ignition system immediately re-established it before the engine could wind down past the point of easy restart. The aircraft could now fire its cannon without risking its own engines, which was a capability that the program had been designed around from the beginning, and that had taken several years and 1 lost aircraft to actually achieve. With the cannon integration resolved, the engineers turned to the survival architecture that would define the aircraft's reputation. The philosophical foundation was stated without qualification in the design requirements. A close air support aircraft operating at low altitude and low speed would be hit by ground fire as a matter of operational routine, not as an exceptional event. The question was not whether the aircraft would sustain damage, but how much damage it could sustain while remaining controllable and returning the pilot to friendly territory. The pilot protection system began with a structure unlike anything previously built into a tactical aircraft. A bathtub-shaped enclosure of titanium alloy, not a thin structural shell, but a genuine armor enclosure with wall thickness at critical points approaching 40 millimeters, surrounded the cockpit from below and on all sides. The weight of this structure alone exceeded 500 kilograms, roughly equivalent to adding 6 adult passengers to the aircraft's payload. It was tested against the primary Soviet anti-aircraft gun caliber of the period and found to defeat it at combat ranges. A pilot sitting inside this enclosure was protected by more armor than most armored personnel carriers offered their infantry occupants. The canopy above this armored tub
was constructed from ballistic glass, rated to defeat small arms fire and artillery fragments, not standard aviation transparency material, but a specialized laminate designed specifically for the threat environment the aircraft was intended to operate in. The fuel system was engineered on the assumption that the tanks would be penetrated. The inner surface of each tank was lined with a self-sealing material that responded to contact with aviation fuel by swelling and closing the penetration, a passive automatic repair system that required no pilot action and no electrical power to function. The interior volume of each tank was filled with open-cell foam that suppressed the formation of explosive fuel vapor above the liquid surface.
The physics of fuel-air explosion require a specific ratio of vapor to oxygen. Too little vapor, and there is no ignition. Too much, and the mixture is too rich to sustain combustion. The foam maintained vapor concentration below the explosive threshold, even when the tank had been penetrated by an incendiary round, converting what would otherwise have been a catastrophic fireball into a manageable fuel leak. Pilots who had taken tank hits in combat described seeing fuel streaming from their aircraft and reaching their home base without fire. The hydraulic system was divided into two fully independent circuits, left and right, each powered by its own engine-driven pump, with the routing of each circuit kept physically separated from the other throughout the aircraft. Every primary control surface, the surfaces that controlled the aircraft's attitude in pitch, roll, and yaw, was connected to both circuits simultaneously. Loss of either circuit left the aircraft fully controllable through the remaining one. Loss of both circuits activated the manual reversion system, in which mechanical linkages, cables and pushrods rather than hydraulic actuators, connected the control column directly to the control surfaces. Controlling an aircraft of this weight through purely mechanical means required physical effort that pilots described as exhausting. But it worked. It worked over Baghdad in 2003, for over an hour, long enough to reach a runway. The landing gear that retracted into wing root pods rather than into the wing structure provided the survival function mentioned earlier. When fully retracted, the wheels protruded slightly below the lower surface of the wing pod, not enough to affect flight performance significantly, but enough to provide a contact point in the event of a gear-up landing. If hydraulic failure prevented normal gear extension and the emergency extension system also failed, a pilot could land the aircraft on these partially protruding wheels rather than on bare airframe skin. The result would be damage to the pod fairings and the wheel assemblies, but the aircraft's structural integrity would survive, the pilot would survive, and the aircraft might even be repairable. A conventional retracted gear emergency landing produces structural damage of a different order. The countermeasures system distributed throughout the aircraft, heat-seeking flares and radar-reflective chaff dispensed from multiple locations on the airframe, was the most extensive installation on any American tactical aircraft of its generation. Sensors monitoring for laser designation and radar tracking signals provided automatic cueing to the dispensing system. Manual backup allowed the pilot to respond to visually observed missile launches. The combination of passive detection, active countermeasures, and structural survivability created a layered defense that addressed every threat category the aircraft was likely to face, not sequentially, as one system and then another, but simultaneously and continuously throughout every mission. The ammunition that the cannon fired gave the aircraft its role against the armored threat that had justified its existence. Standard explosive and incendiary rounds handled soft targets and light vehicles. Against tanks, the aircraft carried a penetrator round whose effectiveness derived from a material property that had nothing to do with conventional ballistics. Depleted uranium is a byproduct of the nuclear fuel enrichment process. the material that remains after the fissile isotopes needed for reactor fuel and weapons have been separated from natural uranium ore. It is not radioactive in the sense that creates immediate health hazards at normal exposure levels, but it is extraordinarily dense, nearly twice as dense as lead, approximately 2.5 times denser than steel. This density is the property that makes it useful as a penetrator material. A penetrator rod of given dimensions and velocity carries kinetic energy proportional to its mass, and depleted uranium carries far more mass per unit volume than any conventional penetrator material. The second relevant property of depleted uranium in penetrator applications is its behavior on impact. Conventional penetrators, including those made from tungsten, which approaches uranium in density, deform on impact with armor plate, the tip of the rod mushrooming outward as the material yields to the resistance of the target. This deformation dissipates energy and reduces the penetrator's ability to continue through the armor. Depleted uranium penetrators behave differently. Rather than mushrooming, the material at the impact interface shears away in small fragments, maintaining a sharp, penetrating tip throughout the passage through the armor. The rod effectively sharpens itself as it penetrates, maintaining its energy-delivering geometry rather than losing it. The practical result is armor penetration performance that exceeds what the material's density alone would predict. The economic dimension of this choice had its own logic. American nuclear fuel production had accumulated very large stockpiles of depleted uranium in storage, material that required ongoing containment costs and represented no useful application in its stored form. The defense industry's use of this material as penetrator stock was, from a resource management perspective, a solution to a storage problem as much as it was a weapons development choice. The military was using material that would otherwise have required indefinite, expensive storage, converting a liability into a capability. The aircraft's first large-scale combat test came during the Gulf War of 1991, when it was employed against the armored forces of the Iraqi military across open desert terrain that bore little resemblance to the Central European valleys for which it had been designed. The open terrain turned out to be even more favorable than the European scenario had been. Targets were more visible, approach routes were less constrained, and the density of anti-aircraft defenses, while significant, was more manageable than Soviet doctrine Warsaw Pact air defense would have been. Over 6 weeks of combat operations, the A-10 force flew thousands of sorties and accumulated a record of armored vehicle destruction that exceeded the contributions of every other aircraft in the coalition. The specific numbers varied across different accounting methodologies, but the broad conclusion was consistent regardless of methodology. No other aircraft type came close to the Warthog's contribution to defeating Iraqi armor. An aircraft that had been designed as a Cold War specialized tool, criticized throughout its development for lacking the performance characteristics of the sophisticated aircraft that the Air Force leadership generally preferred, turned out to be better at its specific job than anything else available. The combat accounts from that war illuminated the survival architecture in terms that no peacetime demonstration could have provided. One pilot absorbed a direct missile hit to one of his engines. The engine was not damaged. It was physically separated from the aircraft, held only by plumbing that had not yet been severed, trailing behind the fuselage on a stream of burning fuel. The pilot flew to his airfield on the remaining engine and landed. Another pilot brought his aircraft home with structural damage to the wing that left a gap large enough to see daylight through from the interior. Ground crews photographed these aircraft as documentation rather than as extraordinary evidence, because the damage they saw was becoming routine. The aircraft went back to war a decade later, in a different environment that exposed different characteristics. The Iraqi desert had been ideal terrain for the weapon the A-10 was built around. Large, visible armored vehicles in open ground, at distances where the cannon's ballistics were optimized. The urban and mountain environments of the subsequent conflicts presented the opposite problem. Individual fighters in close proximity to the civilian population and to friendly forces, where the margin for error was measured in meters rather than hundreds of meters. The A-10 adapted to this environment through qualities that its designers had built in for reasons that had nothing to do with the counterinsurgency mission. Its low airspeed and modest altitude allowed pilots to observe targets with their own eyes, rather than through targeting systems, developing a situational awareness of the ground below that faster aircraft simply could not achieve at their necessary airspeeds. Its loiter time, the duration it could remain over a given area on a single fuel load, exceeded any other tactical aircraft in the inventory, meaning that ground troops in contact with a hostile force could have an A-10 overhead for extended periods rather than the brief intervals that high-performance jets could provide before their fuel requirements forced them away. The psychological effect on the infantry below was documented in accounts from soldiers who had served in both the Gulf and in subsequent campaigns, and it was consistent, regardless of geography or cultural context. The sound of A-10 engines approaching produced a specific response in the people calling for it that no other aircraft replicated. The response was confidence. The particular kind of confidence that comes from knowing that the asset overhead can see what you are pointing at, has enough ammunition to deal with it, and will still be there when you need it again 20 minutes later. The campaign to retire the aircraft began almost from the moment it entered service. Senior Air Force leadership had never been comfortable with an aircraft that was fundamentally incompatible with the culture and priorities of a service that measured progress in speed, altitude, and technological sophistication. An aircraft that was slower than its predecessors, lower than tactical doctrine preferred, and armored rather than agile, represented an approach to air power that the institutional Air Force found conceptually uncomfortable, regardless of its operational effectiveness. The first serious retirement effort argued that a multi-role fighter with appropriate weapons could perform the close air support mission without maintaining a dedicated specialized platform. The argument was superficially plausible. The competing aircraft could carry comparable weapons loads and had access to the same precision munitions. But it collapsed under examination of the specific requirements that close air support placed on an aircraft. An aircraft optimized for air-to-air combat and high-altitude precision strike is not optimized for low-altitude persistent presence over troops in contact. The structural protection that allowed the A-10 to absorb ground fire was absent. The hydraulic redundancy that kept the aircraft flyable after systems damage was absent. The ability to operate from austere forward locations was absent. The alternative aircraft was genuinely capable at what it was designed to do. It was not designed to do what the A-10 did. The Gulf War results quieted this argument for a decade. Then a second major effort emerged, around the most expensive aircraft development program in American history. A stealth, multi-role aircraft designed around the principle that the best protection from surface-to-air threats was never being detected in the first place. The argument for this aircraft as a close air support platform rested on its ability to penetrate defended airspace undetected and deliver precision weapons from survivable altitudes. It was a coherent argument for a specific threat environment: high-intensity warfare against a sophisticated adversary with modern integrated air defense. The pilots who flew the A-10 in counterinsurgency operations responded to this argument
with the practical question that always ultimately determines the value of air power to the soldiers it supports. What happens when the enemy is 20 meters from your own troops? The target cannot be pre-planned. The situation is changing by the minute. And you need an aircraft that can see what is happening and respond to it in real time. The stealth aircraft, approaching at high altitude and high speed, could deliver weapons precisely to pre-planned coordinates. It was less suited to the dynamic, close, ambiguous environment that characterized the conflicts that actually consumed American military attention during the decade and a half after the Gulf War. The cost differential between the two aircraft, expressed as operating cost per flight hour, was significant enough to matter at the scale of sustained combat operations. The A-10's hourly cost running at a fraction of the stealth aircraft's figure. Multiplied across the thousands of sorties that characterize sustained operations, the difference became a budget argument that was difficult to dismiss, regardless of capability comparisons. Congressional intervention blocked the retirement repeatedly. The combat histories of specific engagements, documented cases of the aircraft's survival capabilities, of the effects on enemy behavior produced by the cannon's distinctive sound, of infantry units that had called for support and received it in time because the aircraft could stay overhead rather than departing for fuel, were entered into the record each time the retirement debate surfaced. And they were effective arguments because they were specific and verifiable rather than theoretical. The aircraft, designed in 1966, built to survive a war that never happened, has operated through conflicts its designers could not have anticipated, in environments its requirements did not describe, against threats that did not exist when its specifications were written. It has survived not just the enemies it was designed to engage, but the institutional efforts of its own service to retire it. The soldiers who call for it in combat have made the argument for its continued existence more effectively than any technical analysis, because their argument is not about specifications or cost per flight hour, but about what happens on the ground when the sound of its engines arrives over a firefight. What that sound means, the specific quality of reassurance it provides to people in the worst circumstances that infantry combat produces, is not something that can be transferred to a different aircraft by equipping it with the same weapons. It is the product of everything the aircraft is: slow enough to see, durable enough to stay, armored enough to absorb the consequences of doing so, and present long enough to matter. The aircraft that was built around a cannon too powerful for it to safely fire, that looked like an engineering compromise and turned out to be an engineering achievement, that has been scheduled for retirement throughout most of its service life and is still flying, is not flying because of inertia or bureaucratic dysfunction. It is flying because nothing built since does what it does in the specific situations where what it does is necessary. That is the Warthog's answer to every argument for its replacement. Not a performance chart, not a cost analysis. The memory of what it sounded like, approaching from behind a ridgeline, when the soldiers on the ground had been waiting for it.